And welcome back. As we continue our cosmic journey, let's go ahead and establish how we can relate space-time and gravity. In order to do so, we need a couple linkages, that between mass, space, and time. Newton considers space and time to be completely independent, and that thought really continued to be the accepted view until the beginning of the 20th century. But Einstein showed there is a connection between space and time, and that only by considering the two together as one unit called space-time can we really build up a correct picture of the physical world. The gist of Einstein's general theory is that the presence of matter curves or warps the fabric of space-time. Now, this curving of space-time is identified with gravity. Now, the amount of distortion in space-time depends on the mass of material that is involved and how concentrated and compact it is. Terrestrial objects, such as a book, have far too little mass to introduce any significant distortion. Unlike a book, though, stars produce measurable distortions in space-time. A white dwarf with its stronger surface gravity produces more distortion just above its surface than, say, a red giant with the same mass. And so look at this with some space-time examples to really kind of help illustrate what we're talking about here. So let's illustrate this with this graph to kind of start us off. This diagram shows the progress of motors traveling east across the flat landscape. Now our distance traveled is plotted along the horizontal axis. The time elapsed since the motorist left is the starting point plotted along that vertical axis. So if we look at this from each individual point, if you look at from A to B, so starting at the journey began to here, you can see we drove at a uniform speed. And we know it's uniform because we have a very linear line. From B to C, you can see that the motorist stopped and made no progress through space, only time, because while time is continuing, the distance traveled has not changed. Then from C to D, we drove more slowly because, well, maybe there's a police car behind us, and so we don't have as much of a rapid expansion eastward. So now let's apply this same idea, but in 3 dimensions. Let's take a flat rubber sheet and stretch it over a table. In here we have a trained ant that has no trouble walking in a straight line. To truly see how space-time is affected, let's start with just that rubber sheet and the ant, no other materials. This is really going to simulate empty space with no mass in it. We put the ant on one side of the sheet and it's going to walk in a straight line over to the other side. If we put a small grain of sand on the rubber sheet, the sand will distort that sheet just a tiny bit, but this is not a distortion that neither we nor the ant can measure. If we send the ant so it goes close to but not on top of the sand grain, it has a little trouble continuing to walk in a straight line. Now let's add something with a little more mass, let's say a small pebble. Well, this pebble is going to bend or distort the sheet just a little bit around its position. And if we send the ant to the region, it finds its path slightly altered by the distortion of the sheet. Now this distortion is not very large, but if we follow the ant's path carefully, we will notice it's slightly deviating from a straight line. Now this effect does get more noticeable as we increase the mass of the object. So let's jump all the way up to a massive paperweight. Now this heavy object will distort or warp the rubber sheet very effectively, making the sheet near the paperweight no longer straight. Now when a massive object creates a big depression sheet, the ant, which must walk where the sheet takes it, finds the path changed or warped dramatically. As you can see here in this image, the ant is going to have to continue a straight line, but it's going to have to encounter this large dip that it has to overcome. As we send our ant on the journey that takes it close to but not on top of the paperweight, it has no trouble far away from the paperweight continuing its straight path. But as it nears the paperweight, the ant is forced down into the sag. It must then climb up the other side before it can return to walking on an undistorted part of the sheet. All this while, the ant is following the shortest path it can, but this path is curved by the distortion of the sheet itself. Now the mass associated with the largest concentrations of matter distort space-time, and the shortest, most direct paths are no longer straight lines, but instead we find to be curves. Now how large does the mass have to be before we can measure a change in the path followed by light? Well, the paperweight in our analogy might be something like a white dwarf, or even a neutron star, something that is very dense. The distortion of space-time is always going to be greater near the surfaces of these compact, massive objects than near the surface of something such as our sun. And we know the sun is pretty massive, and it also distorts space-time, but it doesn't have the same compaction that you would see in something as like a neutron star.